Across the vastness of the Milky Way, billions of objects drift silently between the stars. Most remain forever hidden, lost in the darkness that fills the space between solar systems. But a few, a few, are launched outward through gravitational interactions powerful enough to eject them into interstellar space. Every once in a great while, one of these ancient fragments passes through our own solar system. The object we now call 3I Atlas is one of these rare visitors. It has traveled for an unimaginable amount of time, carrying with it information about its birthplace, a star system far removed from our own. Its arrival ignited curiosity, debate, and speculation around the world. But behind the noise lies a remarkable scientific story about the nature of interstellar bodies and the physics that govern them. Before it even entered the solar system, 3I Atlas had already lived a history that no human will ever witness. It was formed in the early days of another star, likely billions of years ago. At some point it was thrown out, perhaps by a massive planet, perhaps during a stellar encounter, and sent drifting through the galaxy. Its orbit is hyperbolic, meaning it is not gravitationally bound to the Sun. This is the signature of an interstellar object, a path that curves subtly as it passes near the Sun, but ultimately returns to the depths between the stars. Only two such objects had ever been observed before, Oumuamua in 2017 and 2I Borisov in 2019. 3I Atlas is the third member of this extremely exclusive group. When 3I Atlas was first detected, speculation quickly emerged online. Could it change direction and head toward Earth? Could it be controlled by something? These ideas gained traction, despite being fundamentally incompatible with physics. A natural object cannot abruptly alter its trajectory. Movements in space are governed by gravity, inertia, and the laws of celestial mechanics. To make a sudden directional change, 3I Atlas would need a propulsion system far more powerful than anything natural. Its path is completely consistent with a passive body moving under the influence of the Sun's gravity. It passed behind the Sun, curved slightly as predicted, and continued its outward trajectory, exactly as calculations showed. Nothing in its movement hinted at artificial manipulation. It behaved as any comet-like body would when approaching a star. Early observations raised questions about its identity. Was it an asteroid-like object, something similar to Oumuamua, or a volatile-rich body more similar to a comet? As more data accumulated, the answer became clearer. 3I Atlas behaves like a comet. It gradually brightened as it approached the Sun. It released gas and dust. It developed a tail. Its composition includes volatiles typical of cometary bodies, although it displays a few chemical differences, such as an unusual carbon-to-water ratio. This is not surprising. Even comets within the solar system show remarkable variety. Some are rich in carbon monoxide, others in methane, others in water ice. There is no single template for what a comet must be. Each originates under different conditions, in different regions, exposed to different histories of radiation and temperature. The same applies to 3I Atlas. One of the most frequently asked questions was, why is the tail visible in some photographs but not in others? The explanation lies not in the object, but in the techniques used to photograph it. Comet tails are faint. They often require long exposures, image stacking, and motion alignment to reveal. When astrophotographers stack many images, sometimes dozens or hundreds, the faint tail becomes visible, while the stars appear as small streaks due to their apparent motion in the sky. In contrast, single-frame photographs, short exposures, or images taken with fast shutter speeds may not show the tail at all, especially when the comet is extremely distant. Thus, the variation from no tail to long tail reflects not a physical change, but a methodological one. Despite its faint appearance in single images, the tail of 3I Atlas extends for nearly 2.8 million kilometers, a number that aligns with typical cometary dimensions. Its greenish glow also caused curiosity. This coloration is produced by diatomic carbon molecules, C2, which glow green when they are energized by sunlight, a phenomenon well understood in cometary science. Many comets have displayed this same color, and it is a natural indicator of certain chemical processes occurring in the coma. Some predicted that the object would fragment dramatically after approaching the Sun, but such an event requires rapid internal heating, pressure buildup beneath the surface, structural weakness, or a composition dominated by volatile ices. 3I Atlas showed none of these characteristics at levels high enough to cause a disruption. Its nucleus remained stable. Its brightness did not collapse. Its tail evolved in a predictable way. It behaved exactly as a small, intact comet should. Its structure was simply strong enough to withstand the thermal stress of perihelion. As with Oumuamua, 3I Atlas attracted attention not only from scientists, but also from the public imagination. Speculations ranged widely: that it was an artificial craft, that it carried probes, that it opened dimensional portals, that it was connected to prophecies or symbolic interpretations. None of these claims withstand scientific examination. The physical behavior of 3I Atlas is fully consistent with a natural object. Its orbit follows gravitational predictions. Its composition matches comet-like bodies. Its brightness variations reflect sublimation processes. Its tail is a product of solar heating. What fascinates astronomers is not what it could be, but what it truly is: a fragment from another star system, offering a rare scientific glimpse into a place humanity cannot yet reach. While 3I Atlas behaves like a comet, it carries unusual signatures: higher levels of carbon, traces of metals like iron and nickel, a mixture of volatiles that differ from many local comets. These variations are not signs of artificiality. They are signatures of its birthplace. If it formed around a younger or older star, or in a colder or warmer region of its protoplanetary disk, its chemistry would naturally differ from that of comets around the Sun. Each interstellar object is a messenger from a different chemical environment in the galaxy. Interstellar objects are more than curiosities. They help answer major scientific questions. How common are comets in other planetary systems? What types of materials exist in different star-forming regions? How do gravitational interactions eject bodies into interstellar space? Could water and organic molecules be widespread throughout the galaxy? 3I Atlas contributes to this knowledge, joining Oumuamua and Borisov as the only direct samples we have of extrasolar matter passing close enough to study. Each observation, imaging, spectroscopy, photometry, adds pieces to a puzzle that spans light years. As it travels outward once again, 3I Atlas will continue to be observed until it becomes too faint for even the world's largest telescopes. It will pass about 270 million kilometers from Earth, around 53 million kilometers from Jupiter. These distances eliminate any risk, but they allow for continued study. The closer approach to Jupiter will provide an opportunity for spacecraft such as NASA's Juno to attempt low-frequency radio observations, potentially the first interstellar measurement taken from another world. After that, 3I Atlas will fade into the background of the galaxy, returning to the darkness from which it came. 3I Atlas is not a threat. It is not artificial. It is not symbolic or supernatural. It is something far más interessant, a window into another part of our galaxy. Its journey through the solar system allows scientists to observe materials that formed around another star, a chance that may occur only a handful of times per century. Every interstellar object enriches our understanding of planetary system formation, the chemistry of distant environments, the origins of volatiles and ices in the galaxy, the diversity of bodies that travel beyond the Sun's influence. The science is not only precise, it is inspiring, because each of these visitors carries a story written long before humanity existed. And by studying them, we take one more step toward understanding the vast, ancient, and complex galaxy that surrounds us.